question 23 then, we're calculating delta H from temperature change. So the key relationship is Q is equal to MC delta T, which you need to know. But in particular, what you need to focus on is making sure that you get the right value for M. And the important thing when you memorize it is don't just learn M is mass, but learn M is mass of the material being heated. And then you've got to picture the experiment and think, well, what is the material being heated? Because that will then tell you how you've got to calculate that mass. So in this case, we've just got a pot with some silver nitrate solution in it, and we're chucking in some magnesium metal. And so you can see, if you do that, that the heat produced in the reaction is going to basically spread through the solution. And therefore M is the mass of the solution. Not the mass of the magnesium, not the mass of the silver nitrate, but the mass of the solution, which is what's being heated up. So that tells us what we've got to try and find, which is the mass of the solution. Now sometimes they give you data where that's actually been measured. You know, they measure the pot with the solution in it, and then they measure the empty pot and you subtract to find out what M is. But in this case they don't. All they tell you is that the volume is 25.0 cm cubed, and you have to turn that into the mass. And it prompts you to do that because it gives you a big clue, which it tells you to assume that the density of the solution is the same as that of water. And what you should have done is thought, why are they telling me that? And the answer is, well, because density relates the mass to the volume. Okay, density is equal to mass divided by volume, and the density is normally given in grams per cm cubed in chemistry, so that means it's the mass in grams divided by the volume in cm cubed. And for water, which it's told you to assume has the same density as your solution, for water the density is 1 gram per cm cubed. Now you have to know this so that you can apply this to the calculation. The density is 1 gram per cm cubed for water, which means that the mass in grams is equal to the volume in cm cubed. Okay, so you need to be prepared to do that kind of calculation to figure out the value of M in your Q calculation there. Okay, so if we just get rid of that, we've then got that M is therefore 25.0 grams. C comes from your data sheet, is 4.18 joules per gram per Kelvin. And delta T is the temperature change. Now don't be fooled by the Kelvin. Remember, the size of a degree Kelvin is the same as the size of a degree C. So a change, delta T, will be the same number whether it's in Kelvin or degrees C. The actual temperatures are different, but the size of the change is the same. So because it's delta T, you don't have to worry about the Kelvin thing. You just say, right, that minus that, 28.0 degrees C is the temperature change, and so 28.0 is what goes into there. So you multiply those three numbers together and you get 2926, and that will be a value of Q in joules, not kilojoules, because you can see that the input unit was in joules, therefore this will be in joules. Delta H, on the other hand, is in kilojoules per mole, so the first thing we can do is divide that by 1000 to then turn it into kilojoules. But that's not delta H, that's just the amount of heat produced in this particular reaction. And what you want to know is the amount of heat produced when the moles shown in the equation react. So we've got to change it from kilojoules to kilojoules per mole. And therefore the next job is to work out, well, how many moles did we have? And of course that's where these numbers come in. You've got the concentration and you've got the volume, so you can work out the moles of AgNO3 is concentration times volume, which is 0.512 times 0.025. Okay, that volume's in cm cubed, so it has to be divided by 1000 to give you that. And that gives you the moles of silver nitrate, which is 0.0128 moles. So now we can calculate delta H, and it's equal to Q divided by the number of moles with a sign. Okay, so it's the heat divided by the moles, but it has a sign which will be positive if it was endothermic, negative if it was exothermic. You know that convention and you've got to apply it here. So because the temperature went up, you know it was exothermic, and therefore it's minus Q divided by moles. So that's equal to minus 2.926 divided by 0.0128. And that comes to minus 228.6 kilojoules per mole. But that's not quite the answer to the question, because that's per mole of silver nitrate. But if you look at the actual equation for the reaction, let's just write it down over here, it was magnesium plus 2 moles of silver nitrate gives you magnesium nitrate plus 2 moles of silver. And the important thing is that 2. Okay, because that means that delta H of reaction, which remember is defined as the enthalpy change when the number of moles shown in the equation react. So we need to know what would the enthalpy change be when 2 moles of silver nitrate react, and so far we've calculated it per mole. In other words, when 1 mole reacts, it will be that much. So we simply have to multiply that number by 2. So we just get times 2 to find delta H when 2 moles of AgNO3 react, as in the equation. And that's going to give us our final answer, which is minus 457 kilojoules per mole. As always, check, see what it says about rounding, and this time it says an appropriate number of significant figures. So why have I rounded that to 3? Well, you look at all the data that went into the calculation, and you say, well, what level of accuracy were those? And generally they're all 3 significant figures. The temperature is slightly iffy, and I wasn't completely sure about this question. If that means they were only measured to the nearest 0.5, then strictly speaking you don't really know that to 3 significant figures, because you don't know it to the nearest 0.1. But it doesn't actually say that in the question. It may just be that they were more precisely measured than that, and that they just happened to both come out at 0.5. So I think we're just going to assume that these are genuine 3 significant figures, and therefore that's what you round your answer to. Okay, so part 2 of that, it's asking us now, how could we confirm that all of the silver nitrate had been used up? And it's suggesting we can do that by adding sodium chloride solution. And of course what it's getting at here is this reaction, which is much easier to write just with an ionic equation. It's really not worth writing a full equation for this, because for a precipitation reaction the important thing is positive ion meets negative ion, and they like each other and they stick together and they fall out of solution and form a solid. So that's all you need for the equation for the reaction. And the point is that you would see it because a white precipitate would be formed. Remember, you need to learn the colours of these silver halide precipitates, but the chloride one is white. And you just need to explain that that would only happen if there was residual silver ions in the solution. If all of the silver ions have reacted, then there wouldn't be any left in the solution, and therefore you wouldn't see a white precipitate. And you need to spell that out. Okay, make sure that it's clear that you wouldn't see the white precipitate if, as we expect, all the silver ions have reacted. Okay, so part B is Boltzmann distribution. So you absolutely have to learn this graph and learn what it means. So the axes are energy. You can put kinetic energy if you want, but you don't need to. Energy is enough. And this is the number of molecules on this axis. So those both have to be clearly labelled. And then the shape of a Boltzmann distribution, the important features are, first of all, it starts at 0, 0. In other words, 0 molecules have 0 energy, and it has a shape that rises to a peak and then comes down asymmetrically, so it comes down more gradually on that side, and you have to draw it so that it doesn't touch this axis. Okay, in reality it's asymptotic, which means it gets closer and closer but never quite meets it, but they want to see that you know it doesn't cross it, so best thing to do is leave it like that so that it clearly isn't going to slam into that axis. So that's one Boltzmann distribution. In this case it wanted you to explain what happened if you changed the temperature. So what you have to remember is that if you increase the temperature, the distribution of energies is going to shift towards higher energy. So the position of this peak will be further to the right at higher temperature, because the average energy of a molecule, okay, the peak is the modal energy, if you like, one of the average ways of measuring an average energy, and the average energy is going to be higher at higher temperature. So the peak's going to be further to the right, but because the area under the curve represents the total number of molecules in the system, that can't change. So if it's more spread out in this direction, it has to be flattened in this direction. And those two things have to be very clear. So make it really, that's perhaps a funny shape, but it needs to be very obvious that this peak is further to the right than that one, and that it's lower than that one. Don't sort of make it so close that they have to get a magnifying glass out to see whether this peak's slightly further to the right than that one, because they won't bother. It needs to look very clear like that. So those are your two curves. You need to label them clearly. It's best not to use sort of coding, because obviously you can't use colours in the exam. You could possibly do it with dotted lines and full lines or something, but the easiest thing is just to label them and say that's the low temperature and that's the high temperature, and then it's nice and clear. Okay, so those are your two curves. And the important thing is that the activation energy is just one value of the energy, so it therefore corresponds to a line like that, which again you need to label. And that's all you need on the diagram, except that the way to make best use of the diagram is to shade the areas in to the right of the activation energy. So at low temperature there's just this rather small area, and that represents the proportion of molecules. In other words, just this area as a fraction of the total represents the proportion of molecules which have enough energy to react when they collide. At a higher temperature you can use a different shading to make the point that it's now that much bigger area. So a much bigger proportion of molecules have enough energy to react when they collide. So then you've got to put that into words, because that's what you need on the diagram. But I think the thing to do is to explain that what these areas represent. So the proportion of molecules with sufficient energy to react when they collide is greater at high temperature, as shown by the bigger shaded area. That's really how you relate it to the diagram. So the proportion of molecules with enough energy to react when they collide is greater at high temperature, as shown by the bigger shaded area. And then you've still got to follow that up with more, because they'll say, yeah, well, why should I care about that? And you have to say, therefore, successful collisions will occur more frequently at higher temperature. People often lose that mark because they say things like, you get more successful collisions. But you've got to get that time element in there. Obviously, how many you get depends on how long you wait. So it's not the number, it's how frequently they occur. So therefore, successful collisions occur more frequently at higher temperature.